Hello and welcome to this presentation about reducing vehicle system level software test effort. That's a long row of words, but I promise I will explain each and every of them during this presentation. My name is Daniel Flemström and I'm a PhD student at Mälardalens Högskola in Sweden. And yeah, let's go. Starting with outline. So this talk is divided into 4 pieces. It's a scope and background, where I give you some basics you need to understand the results that I will present next. And I will select 2 of the results from this work. I will then continue with some conclusions for this. And then in the methods section, I will talk a little bit about how this research was performed. So, as promised, I will sort of go through each of the words in the title and then introduce some other background information that you will need. So, starting out with software test effort, I will talk about what I mean with that and the meaning of that in this context of this thesis. I'll also talk about reduction, what that means in this context, and also the system level. I mean, what is the system level and how does that affect what we are doing? And also the vehicle software system. Beginning with the first word, software test. So what does software testing mean in this context? Obviously, that means that we are doing some tests on software, but we need to develop that a little bit more. So if we start out with what we are testing, so that is what we call the system under test, the SUT. And basically what you do when you test things is that you send in a bunch of stimulus. For example, you push buttons and you pull levers and things like that. And then you wait a little bit and then you observe how the software responds to this stimulus. And as you can see, this can be done manually, as sort of exploratory testing, or you follow a protocol and you do this, or you can do this automated using a script and a computer that sends stimulus to the system and observes the reactions. So this means that what I am sort of studying in this context is sort of writing these tests, how to automate them and when to automate them. Also how to execute this, and that especially for automated testing. It's interesting. And I also studied about how to analyze the results of this testing. Why would we even do this? Well, first of all, software testing is almost 60% of the development cost for a software, or up to. So this means that if we can sort of reduce that part of it, there's a lot of money to get there. But also, this is by necessity, because the systems get more and more complex, and there are more systems that interact with other systems, and you need more combinations that you can test with these systems. So the amount of required testing is exploding. So we need to do this in a smarter way. And the what we are reducing, is what I said before. It's the writing of test cases, automating, executing, and analyzing. So these different activities I'm studying to see, can we do something in each and every of these corners? And of course, how would this be done? Well, actually there's 2 paths. One is to be more efficient. So you do things quicker, you do things maybe in parallel, or have better tools and so things like that. Or you simply do less. And that could be that you realize that I have already done this before, so let's not do it. So by doing less, or by knowing what you've already done, you can just skip doing things. The next part is to understand what the system level means. And when you develop larger systems like a train or a car, you need to have different levels of abstractions. And you also need a strategy to break this down into small pieces that you can manage. And then you have to have a strategy to systematically assemble these pieces, test them, and eventually ending up with a fully functioning train that you can run on rail. And usually you use something called the V model. And this is an illustration of the V model with 3 levels of abstraction. So at the top level you have the vehicle level, where you specify the overall vehicle behavior and the software requirements, and you have, for example, acceptance tests and user tests for the entire vehicle. At the next level you have, for the system level, you describe each subsystem, how the things should work together, for example the braking system and the door system and so on. And then you go into more and more detail to have the lowest level, that's a software level or a unit level called. Yep. So at the lowest level you have individual software units that you can test on a single PC, for example. It's very limited functionality, and you can develop this in different offices or even different countries. And then as you move up on the right side of the V, you integrate these with different strategies, and you get a bigger system, which you test during each of these intermediate levels. And then you end up with a fully functioning train. And as I said, the focus of this thesis is the system level, where you can see it as you have larger components, you have subsystems that you test, and you can integrate them, or it could be also the whole system, the system as a whole. Well, if we remember the previous picture that I showed, we have a system under test that we said, okay, so this is a system or a subsystem in this V model. We send in stimuli and observations, and we do some manual testing or automated testing. And still, I'm studying the writing, automating, analyzing, and execution of it. However, this was not the entire truth. What we need to have stubs and models of the other parts of the system that is not already implemented. And also, here is the big difference. Typically at the system level, we interact with the physical environment. This could also be a model of the physical environment. Also in the system level, you can do this on hardware or in simulators in different grades. And often you have a test framework that abstracts this away. As a tester, you still do manual testing or automated testing. The test framework would then adapt how to send stimuli and observations to the system under test, depending on if it's hardware or if it's running in a software simulator. So the last word in the title, that would be the vehicle software systems. So what is that? So in short, a vehicle software system is a program that runs in a car or in a train. And it differs in some way from like Word or PowerPoint that you run on your PC. And this is also why testing these systems differs a little bit. So if we start out with what you're used to in the PC, you typically have the keyboard and you have a mouse, and you text things in, and you click with the mouse and you do some processing, and then the result comes on the screen. So the input to the program is quite a limited set of inputs. It's a mouse, it's a keyboard, and it could also fetch information from other systems for that part. But the key thing here is that you get the response on the screen, and sort of everything that happens, it's just software. Typically, I mean, if you misspell in Word, or if Word hangs, you lose the document, but hopefully you're not using your life. If you take a look at Vehicular software, on the other hand, we can note that you typically have a lot of different sensors. Still, some of them is operated by you, so you can still give input, but you also have a lot of other sensors that takes the environment into consideration. And the more modern system you have, the more demands you have on the system should be able to take actions on this input independently. And finally, the most important difference is that these vehicular systems, they typically have sort of effect on the real world. So they move things, they activate the brakes, they activate brake lights, they help you to turn the wheel, or raises the pantograph on a train, or open doors. So this poses a set of other criteria on both the hardware but also on the programming. So while a desktop system needs to be fast, a vehicular software system needs to be deterministic. So you need to know how long time things takes, and if we take the extreme example of an airbag, it shouldn't be too quick, because then it's inflated and deflated before you hit it. It must be exactly the right thing. Also, it must be very, very, very accurate, and you need to make sure that everything works sort of the same way all the time. So you can't have that much complexity as you have in the desktop system, because you can't guarantee that it's working. So this means that the programming model is a little bit different. So I guess you have all seen a computer program for a PC with C++ or JavaScript or something like that. Typically in vehicular software systems, they often use something called function block programs. So these systems are, first of all, they're based on signals. So from each sensor you can read a signal. It could be a continuous value, or it could be a binary value on or off, but it's all about the signals. And to the left you see they have 5 signals coming into the program, and these are read at the same time in a cyclic fashion, like 64 milliseconds. Then you have a number of elements that you compute the output from, and then all of the outputs are computed and sort of presented at the same time. So this means that each 64 milliseconds you recalculate the results of the outputs from the inputs. And this gives a much more precise determinism than you have in a desktop system. Also, you can sort of, if it's really, really critical, it's much more easy to sort of create mathematical models to verify that it will work. Awesome.